the question I have is this, that we do like discussing modifications to quantum mechanics, and especially connected to gravity. But what I don't see is how any modification to quantum mechanics will solve the high energy problems of gravity. So what is the likelihood that we'll solve the high energy problems by doing some low energy modifications? It's a general topic of discussion.
So just to repeat the question, will modifying quantum mechanics at low energies solve the high energy problems of quantum gravity? Well, I think a number of people here have probably thought about that. I'm guessing Bob might have. No. And I suppose that part of the answer to that question for those who are following the debate yesterday about the black hole information paradox is whether the black hole information paradox contains elements of high energy quantum gravity or not. I can certainly say that from the point of view of the CWL theory, this is a question that Abbe already asked. He said, does CWL theory say anything about what happens at the Planck energy? And the answer is no. It certainly may well say something about what happens at 10 to the minus 10 of the Planck energy, or maybe even 10 to the minus 5. But it's not supposed to be extrapolated to the Planck energy. And in fact, I would ask you a question, John. Up to what energy do you trust the effective field theory of quantum gravity?
That depends on things that I don't know. So I would trust it probably to the weak scale at the moment, because we've done physics to the weak scale. But who knows? We could in the next decade of energy find out that the world is really 5-dimensional instead of 4, and then I wouldn't trust my calculations. So something can happen at the next, just around the corner. Where do I really think it probably is? I don't think there's probably another dimension at 100 TeV. I don't think there's any reason why it has to fail before the Planck scale. It doesn't have to fail, but it easily could.
Right. So I mean, I guess I completely agree with you. There's 16 orders of magnitude of energy between what we've done experimentally and the Planck energy. And if past history is any guide, there's no particular reason to suppose that something new might not happen in that so-called desert.
Absolutely.
And of course, the assumption behind a lot of the high energy theory is that nothing happens in that desert and that we can extrapolate all the way up to the Planck energy. Would that be fair?
I'm sure there are some that way, but others have scales along the way.
Yes, well, sure, of course, yeah.
And so.
Right. So, Cliff. Oh, yeah, good.
So if I understand the question correctly, it's if you sacrifice unitarity in quantum mechanics, could that buy you anything for the UV problem, for UV completion?
For example?
So I think there's probably a fair number of examples where that actually happens, right? So, okay, I got music now. So, like, as you know, for R squared or conformal gravity, you pay the cost of additional ghosts. If you don't care about ghosts because you don't care about unitarity, then it's fine. There's lots of papers where they have higher curvature terms with this like low pass filter, where they have like a f of box acting on Ricci curvatures, and those have crazy unitarity properties. The Feynman path integral doesn't give you unitary Cunning rules, but they have very good ultraviolet behavior. So I think once you relax quantum mechanics, you don't worry about unitarity or probabilities summing to 1. I think you actually have a fair amount of freedom. That's what I would say. Yeah. The example being conformal gravity.
Yeah, I'm not as much sure that they're sacrificing quantum mechanics. I mean, you're applying the same rules as usual quantum mechanics.
Well, they use a path integral, and they have additional modes which are ghost-like, which
Right.
induce negative probabilities. So I consider that, that's not quantum mechanics. Yeah. But as soon as your norm squareds are not positive definite, then I would say you're
Yeah,
outside that regime. Yeah.
I'm not sure that's the right interpretation of those. But
Well, it's the common one for, say, Lee Wick.
it's
or-
a common one.
Yeah, it's the common one, yeah. So maybe you're saying it's possible that you could do a contour or Wick rotation, which eliminates those modes, but no one's constructed that beyond one loop for even the simplest theories. So barring any kind of miraculous choice of contour to eliminate those ghost modes, I think most people think it's not. But I agree, it's not a resolved issue from that point of view. Yeah.
First, I thought we were being locked in. But apparently not. Sorry, did you want to go on further on that, John? Okay. Other comments, questions? Yes.
Perhaps I can make a comment on just about like a situation or a scenario where relatively standard quantum theory is applied to great success, to extraordinarily high energy scales. Namely, that's the very early universe when you start talking about inflation and the program of cosmological perturbations. Now, it comes with the caveat that, well, in order to believe these calculations, you have to believe that inflation happened, and I mean, there are proposals to test this, but yeah, I just want to toss that out there as like this is a situation where, in fact, you get like so the relevant cosmological length scale, the Hubble length, this in early universe inflation for the modes that are relevant in what we see in the night sky today is only about 6 orders of magnitude below the Planck length, and the theory of cosmological perturbations works very well at predicting, or at, I guess, retrodicting what we see in the sky, the statistics of the CMB.